Okay, good morning. Okay, so today we're going to cover a few things. All right, so firstly, we're going to go through today's lecture, which is on scheduling. All right. After that, we are going to discuss about the project assessment. Okay, next week. All right, and then also the exam. The concept of how the questions will be asked. All right, so these are important things. Okay, both for next week as well as the exam. All right. So along the way, again, if you have questions, the poll is always active. Okay, so if you have questions, you can put your questions there. All right. So I hope all of you have checked your midterm result as well. Okay, together with the answer script. So if anything you're not sure, okay, why the answers are as such, you can come and ask me. Okay, I'll explain. But I think in the answer sheet I provided, I have given the explanation for every answer, so you understand the rationale behind the choices. Okay. Okay, so some of you asked me how come the midterm paper looks quite different from the previous batch. Okay, questions are different. All right. So usually I try to set quite similar style. Okay, but this particular year, your batch, why is it a bit different? Okay, why it's different is because during the recess week, on one of the nights, I couldn't sleep. Okay, so I woke up just before midnight, and I decided not to waste my time, so I spent 3 hours setting a paper. Okay, so that's why it looks quite different, because I had a lot of time to think throughout the night. Okay, and the same thing happened 2 days later, so I used that time to set the exam paper. Okay, so both your papers were set in the middle of the night. Okay, because I couldn't sleep. All right, so exam, no worry, we will go through the exam format and how it's going to be like later on. Okay, so let's come to the topic first, scheduling. Okay, so this particular diagram, correct, state transition diagram, we have seen this before, correct? So you understand that whenever I create a new task, that new task enters into a ready state, correct? And inside this ready state, we have a list of tasks, correct? And okay, and what we do is we say that the highest priority task transitions to the run state, correct, based on the preemptive kernel that we have. All right. So now we are going to explore this a bit more on how this decision is made. How do we schedule tasks to ensure that they transition correctly, and at the same time we fulfill the deadlines of the system. All right. So today's topic is all about scheduling concepts. All right. How we are able to schedule tasks. All right. And basically what we are saying is we want to have some set of rules or a policy in place such that when I schedule my tasks, I can fulfill the deadlines that I set aside for my tasks. All right, so let's look at a simple example here. So let's say I have these 3 tasks, A, B, and C. All right, and let's just say I randomly select, correct? I say A first, B first, followed by C. All right, so the concept here is that all the tasks are ready at the same time. That means T equals to 0. All the tasks are ready. Okay, execution time is basically the time that I need to compute or finish that task in terms of the computational time needed. Deadline is the time by which I must complete the computation. All right, so if I go in this sequence, A, B, and C, okay, what do I have? So let's say A runs first, followed by B, followed by C. Okay, if I go in this sequence, what happens? All right, if you look at the deadlines for all 3 of them, you will see that B will miss the deadline. All right, that means if I say that when the task, from the time that it becomes ready, I must be able to complete within my deadline. So in this case, the deadline for B is 20 milliseconds, all right, but I finish only at 30 milliseconds here. Okay, so we say that B missed the deadline. All right. If I go in another order, okay, so again, we are just trying some random orders, B, A, C. Okay, so B, A, and C. And if I look at the deadline, all is good. All the tasks can meet the deadline without any issue. All right. So again, another order, B, C, A. What do I get? I have B, C, and A. And I see that A will miss the deadline because A's deadline is 50 milliseconds, but A only completes here at 60 milliseconds. All right. So of course, this is just to illustrate the fact that I can randomly try, and maybe I have one particular sequence that works. Okay, but of course there should be a proper approach to this, which is what we are going to explore here. All right, so in this lecture, okay, there is some terminology you must be familiar with, okay, and at the same time, there are certain assumptions that we will make. All right, so these assumptions may not always hold true in a practical scenario like what you're doing for your project, but for the analysis, okay, to understand how these concepts come about, we will make these assumptions. So we are following with some of these rules. Okay, so firstly, we say that we have a fixed number of tasks, which is n, and we also say that tasks are periodic in nature. Now, generally, are your tasks periodic? In a sense, they are, because you write them as an infinite loop, correct? Okay, so all your tasks are written as an infinite loop. Only thing is, they may not actually be periodic in the sense that we know it, correct? Like how a sine wave is. Okay, we say it's periodic in a sense that whenever the event triggers it, or some semaphore is released, or some flag is set, then I go ahead and do it. All right. So we say that tasks are periodic in this nature. All right, and every time I release a task, the task itself has a deadline. All right, so that deadline is effectively the period. All right. Now, the next term is WCET, C, okay, in short, where it's called the worst case execution time. And what we are saying is that every time I run an instance of a task, I may execute it for a different amount of time. Okay, why is it different? Because your code can have if-else statement, can have loops. So at one time you run, you execute the if block, another time you execute the else block. Sometimes the loop runs for 10 times, sometimes it runs for 100 times, and so on. Okay, so each instance of the task executing, you may have different time duration where the task actually runs. Okay, so you can see here that each instance has a different duration. All right, so that is the worst case execution time. Okay, and as we said just now, a task will also have a deadline. Okay, that means I need to fulfill the computational requirements by the deadline. Okay, and since we also say that tasks are periodic in nature, we can simplify this to say that the deadline is the period. All right, since I'm going to release the task, for example, let's say every 1 second, the moment I release the task, by the next 1 second interval, I must finish whatever I need to finish. Correct? Because the next instance is going to be released. All right, so to simplify this, we can say that the deadline is the same as the period. So every periodic interval is actually the deadline itself. Okay, by that time, I need to finish whatever I need to do. All right, now some other additional assumptions, okay, that the tasks are independent of each other. Again, like I said, this does not hold true in our practical sense when we do the project and so on, because there is a dependency on some resource being allocated, some flag being set, and so on. Okay, but for this case, we will assume that all the tasks are independent, okay, of each other. All right, and we do not factor in any scheduling or context switch overhead. Okay, so we have seen worst case execution time. Again, that is based on the code itself, okay, the flow of the code and which particular flow will give me the highest amount of execution time. But we also know that we are dealing with a preemptive kernel, all right, which means that while I'm running, I may get preempted. Correct? So because of that, there is always this concept of preemption or interference. So that leads us to another term, which is WCRT, worst case response time. Okay? So what is worst case response time? That is taking into account the interference or the preemption of a higher priority task. Okay, so for example, in this case, when task 1 is running, there is a preemption here by task X. Okay, so during the periodic interval, task 1 is running, but task X, which is higher priority, takes over momentarily the CPU, and then only task 1 can resume. Okay, so because of this preemption or interference, we have more challenges to deal with, correct? Because there is a chance that this higher priority task that takes over the CPU extends to the point where my actual task cannot run and I'll miss the deadline. Okay, so this is what is happening here, where task Y preempts the task 1, and then task 1 misses the deadline. Okay, so let's understand this. So we can see that because we are dealing with the kernel which is priority driven and preemptive in nature. Okay, anytime that a task is running, a low priority task is running, a high priority task that gets ready will automatically be allocated CPU time. Okay, so this is actually what we are seeing with our own KL25Z board. All right, so let's look at how something like that will play out. So let's say I have these three tasks, correct? T1, T2, and T3. Okay, T1 is high priority, medium priority, and low priority. And let's just say that at T1 and T3 at time t equals 0 is in some block state. Okay, so when you say it's in a block state, means what? That means it is not able to run because it is waiting for some resource to be allocated. Okay, so T2 is the only one that is able to run, and T2 is running. Okay, and at some point of time, all right, T1 becomes ready. So since T1 is higher priority, what will happen? I will have to do a context switch. All right, so I'll have to preempt the kernel, and T1 will run. So at this point of time here, okay, in the ready queue, T2 will be shifted back here, correct? So T2 is not blocked, but it's ready. Okay, it's ready because it was running and it was preempted. Okay, you go to block when you are running and you cannot get something that you want. Okay, in this case, it is not the case. It is a case where T2 had everything, but because a higher priority task came along, T2 is switched back to ready state and T1 takes over the run state. Okay, so that is what's happening first. And subsequently, let's say T3 also becomes ready. Okay, but T3 is low priority, so T3 also joins the queue. Okay, so T3 also joins the ready queue. So both T2 and T3 will be in the queue until at some point of time when T1 gives out the CPU. All right. So when you have priority-driven scheduling, it is important that your high priority tasks have some mechanism to give up the CPU. If not, you will hog the CPU forever. Correct? Even in your RTX, it's the same thing. Correct? If one of the tasks is high priority and you make it run forever, it will just run forever. Okay? So you must have some mechanism in place on how the other priority tasks will still have CPU time. All right. So in this case, let's say T1 goes to a block state or goes to a block state that allows other tasks to run. So that in this case, T2 will get a chance to run, and after that, T3. Okay. So that is how the transition would have happened in this case here. All right. So now comes the important thing. Correct. So since we know that priority is very important, how do I assign priorities? Okay, so we're going to spend quite a lot of time on fixed priority first, okay, to understand that if I assign some fixed priority values, how will the whole system play out, and then we will have a small example on the dynamic priority as well. Okay, so the most popular algorithm, okay, which is also very easy, okay, is what you call the RMS, okay, rate monotonic scheduling. Okay, RMS also got another meaning in engineering, correct? What is that? Your root mean square, correct? Okay, so in this case, RMS is your rate monotonic scheduling here in this scheduling theory. And the concept is very simple. It is basically saying that priority is inversely proportional to task period, which means what? If my task period is very short, means I need to run very frequently. Okay, so since I need to run very frequently, I need the CPU's attention a lot. Okay, so since I need a lot of attention, my priority is very high. Okay, if I have a lot of time, my period is very large, means I can take my time. I don't need to be so important. Correct? If I am having a very short period, that means my frequency is very high, so my attention of the CPU is also very high. All right, so as long as my priority is inversely proportional to the task period, we are following this algorithm here. All right, so if I look at these three tasks over here, T1, T2, and T3, okay, so based on RMS, we can say that T2 is considered high priority, this is considered medium priority, and this is considered low priority. Okay, just by following RMS. So let's see how this whole thing will play out over time. So at time t equals to 0, all the tasks are in the ready state. Okay, all the tasks are in the ready state. And since T2 is the highest priority, T2 will run first. All right, so each block here represents 1 unit of time. So in this case, T2 is only occupying 1 block or 1 unit of time. So once T2 finishes, we can transition to T1. Correct? So from T2, we go to T1, and T1 takes 2 units of time. And once T1 finishes, we have a slot for T3. Okay, but T3 itself requires 2 units of time. But before I can finish, what happened? The next interval of T2 kicks in. Alright, because T2 repeats every 4 units of time. So since the next interval of T2 kicks in, okay, I will have to preempt T3 and jump to T2. Correct? So I'll run T2 for 1 unit. Okay, and once I finish, it is just nice for the next interval of T1, because T1 is every 5 units. Okay, so T1 will run, and eventually I have another free slot for T3 to finish. Okay, when T3 finishes, again the same thing. Okay, T2 runs again. Okay, 1 unit of time, and after that there will be T1. Okay, so it is not always that every task is running. So for example, over here you can see that there is actually a gap. Correct, so this is 9 and this is 10. Correct, so from unit 9 to 10 there is actually nothing running. Correct, because based on the time interval, okay, and the scheduling of the task, there will be some blocks of time, for example, where there is no task that is running. So 9 to 10 there is actually nothing running. Alright, now after T1 runs, again the next interval of T2 kicks in. Okay, then again you can see there is some gap here where there is no task running. Alright, so at this time T equals to 15, there is 1 instance of T1. Okay, but before T1 can finish, there is another interval of T2. Alright, because every 4 units there is T2 repeating itself. So T1 will be preempted and then T2 will run. Okay, and after T2 runs, then I can go back to T1 and can continue. Alright, and the next periodic interval is where T2 starts again, and once T2 runs 1 unit, then T1 followed by T3. Okay, now if you look at this whole sequence, you will see that this initial block here matches this initial block here. Alright, what we saw in the first few seconds at time t equals to 0 matches the same timeline or behavior at time t equals to 20 onwards as well. Alright, so what does this tell us? That means from 20 to 40, the sequence is going to be the same as 0 to 20. Correct, because the whole sequence is sort of repeating itself. Alright, and that is what we call the hyper period. Okay, so the hyper period is this term which is used to describe the behavior of the task over an extended period of time, and that hyper period repeats itself. Okay, now how do I find out this hyper period? Is basically the LCM of the task periods. Okay, so given any number of tasks, you just find the LCM of the task period, and that is the hyper period, and the important thing is it repeats itself. Now, why do you want this hyper period? Why do you want to analyze this hyper period? Because if within this hyper period, I can analyze and I can see that no deadline is missed. Okay, if there's no deadline that is missed within the hyper period, then we can safely say that this task set is schedulable. Okay, that means it will keep repeating itself, but there will be no issue because I will not miss any deadline. Okay, so that is the task or the term hyper period. Okay, so what is a feasible schedule? A feasible schedule, okay, is one where we can meet all the timing constraints. Okay, you want to meet all the timing constraints, and a scheduling algorithm that we choose is the one that produces a feasible schedule if it exists. Okay, if it exists, all right. So in some cases, a feasible schedule may not exist. All right, so we want to analyze first to see whether such a schedule exists, and then we work towards choosing the appropriate algorithm for that. All right, so RMS is basically called an optimal fixed priority scheduling algorithm. All right, now what do you mean by this? Okay, so for any n number of tasks, okay, we have n factorial ways of assigning priorities. Okay, that means if I say I got 3 tasks, T1, T2, T3, I have 6 different ways of randomly assigning priorities. Okay, so let's say these are the 6 different ways of randomly assigning priorities for all the tasks. Okay, now what does RMS tell us? That means if I brute force my way, okay, I just say I try all 6 possibilities. All right, if I try all 6 possibilities, maybe, okay, I may come across 2 that work. Okay, I may come across 2 that work. Okay, and what we are saying is one of it will definitely be RMS. Okay, so you don't need to try your luck or try any other way. If you want to use fixed priority algorithm, you can just stick with RMS and it is guaranteed to be one of the ways that work. Okay, you may find some other sequence that also work. Okay, but RMS is guaranteed to be one of them. Okay, that's why it's called the optimal fixed priority scheduling algorithm. All right, so let's look a bit more, okay, into this concept of schedulability analysis. All right, so you want to analyze the system, okay, based on its what we call worst case behavior, and whether with the worst case behavior we can still fulfill the timing requirements of the system. Okay, so first thing is, like we said just now, we first need to know whether such feasible schedule will even exist in the first place. All right, and that can be measured using this very simple formula known as utilization. Okay, what is utilization? It is basically telling us how much of the processor we are actually using. Okay, and how do I compute that? Very simply, you take the summation of each task computation time over the periodic interval. So in this case, 2 over 5 plus 1 over 4 plus 2 over 20. All right. Now when I add up all of this, in this case I get 0.75, which means what? That means I'm using basically 75% of the processor time. Okay, so based on this sort of very simple metric, I can say that I'm utilizing 75% of the processor time. All right, and this tells us one thing, all right? You only have 100% of your processor time. Okay, you only have 100% of your processor time, which means that if your utilization is greater than 1, then it's not possible already, correct? That means you're trying to run too many things with too much constraint. So you need to loosen up something. Okay, so as long as utilization is lesser than or equal to 1, then your task set is still schedulable. Okay, now this is again some terminology. Okay, so U less than equals to 1 is necessary. Okay, necessary means you must have this condition, you must fulfill this condition, but it is not sufficient. Okay, it is not sufficient. What do you mean by not sufficient? That means it is not enough. Okay, it's not enough for me to say that just because I fulfill this condition, task set is schedulable. Okay, it's necessary, but it is not enough. Okay, so I still need more checks. Okay, more ways of checking this. All right, so let's see an example of this condition where your utilization is lesser than or equal to 1, but it is still not schedulable. All right, so in this case, I have 2 tasks. Okay, and these are the numbers. And if I measure the utilization, that means if I take 2 over 5 plus 4 over 7, I will get this, 34 over 35, all right, which is lesser than 1. All right, so based on the utilization metric, it is satisfying that metric. Okay, but if I try to draw out the 2 possible scenarios, okay, so if I run, let's say task 1 first, okay, if I just follow RMS, I say run task 1 first, okay, then followed by task 2, then task 1 deadline will be met, all right, but then task 2 deadline will be missed, all right, because task 2's deadline is I must complete 4 units by 7 units of time, all right, but then I will miss the deadline over here. Okay, so this is one scenario, correct? But we can also try the other way. Let's say I run T2 first. So if I run T2 first, T2 can fulfill the deadline, but T1 will miss the deadline. Okay, so you can see that even in this simple example, even though my utilization metric is fulfilled, okay, it is still not schedulable. Okay, it's still not schedulable. All right. So this is what we say, where a task set may or may not be schedulable, even if the utilization is lesser than 1. All right. So how do I do it? How do I confirm whether it's schedulable? Okay, we can do like what we did before. We say assign priorities according to RMS. We look at the whole layout for the hyper period. Okay, and if within the hyper period there is no deadline that is missed, then we say it's schedulable. Okay, so that is one way of doing it. All right, but okay, so again, if I apply that principle here, and I say let's look at the hyper period. Okay, as we saw just now, based on RMS, T1 is considered high priority, this is considered low priority. So T1 runs first, followed by T2, and eventually we see that T2's deadline will be missed. Okay, so even though the utilization metric is fulfilled, okay, we can say that this task set is actually not schedulable. All right, it's not schedulable. All right, so of course, trying to draw this for a huge number of task sets is very tedious. All right, so we're going to look at some other metrics, okay, on how we can further analyze this in an easier way. All right, so there's another metric or another parameter we can compute, which is what we call the utilization bound. Okay, so this utilization bound is a number, and as long as my utilization is lesser than or equal to the utilization bound, then we say that it is a sufficient condition. Okay, it is a sufficient condition, but interestingly, it is also not a necessary condition. Okay, so I know it's becoming like a law class, correct? All the terminology. So what is sufficient, what is necessary, what is not necessary? So in this case, when we say it is sufficient means what? That means if I fulfill this requirement, it is enough. Okay, if I fulfill this requirement, then I don't need to check anything else. It is confirmed to be schedulable. But it's not necessary means even if I don't fulfill, it can still be schedulable. Okay, that's what it means. That means even if I do not fulfill this requirement, it can still be schedulable. All right, so how do I compute this number? So n is basically the number of tasks. Okay, so n, it can be 1, can be 2, can be 3. So this table just gives you all the values. Okay, but if you just plug in n equals to 1, n equals to 2, you will get all this. All right, so this is basically the n value. Okay, so this just gives you n value for the most commonly used numbers. Okay, so let's look at a simple example. Okay, where I have two tasks, T1 and T2. So based on the utilization bound formula, using n equals to 2, I say that the utilization bound value is this. All right. So if my utilization, if the utilization that I compute is lesser than 0.828, lesser than or equal to 0.828, if this was the case, then I don't need to worry anything else. All right. I can straight away say that this task set is schedulable. Okay. But the value that I get for utilization is this, which is greater than the bound. Okay, it's greater than the bound. So it may or may not be schedulable. All right, because I do not fulfill this sufficient condition, but it's not necessary. All right. So how can I still verify it? One way is I can draw out the hyper period. Okay, so within the hyper period, we can see that both task 1 and task 2 are able to fulfill the deadline. Okay, and because it can fulfill the deadline, we say that it is still RMS schedulable. Okay, so this is an example to show that even if I don't fulfill the utilization bound, okay, I can still be schedulable. Okay, so this is a quick summary where we are. Okay, with these parameters. Okay, so the two extreme case is easy. If my utilization is greater than 1, we can say for sure not schedulable, right? Because you only have 100% of your processor. Okay, you don't have more of your processor, which means that as long as utilization is greater than 1, there is no way I can schedule all my tasks, okay, with the current constraint that I have. Okay, so that is clear. The other extreme is I fulfill the utilization bound. If I fulfill the utilization bound, then also I can straight away say that it is definitely schedulable. Okay, it's definitely schedulable. I don't need to think or worry about any other parameter. Okay, the only thing right now is what is in between. Correct? What is in between? So what is in between is this case where my utilization is greater than my utilization bound. At the same time, it is smaller than my 1. Correct? That means I fulfill the necessary condition. Utilization is smaller than 1. Okay, but it is greater than my utilization bound. So it is the in-between area, the gray area where I may or may not be schedulable. Okay, so this is the area that we still need to look at a bit more closely to know whether this task set is still schedulable or not. Alright, so let's look at this, where we are going to look at the what we call rate monotonic analysis, which is schedulability analysis to make sure that I meet the necessary condition but not the sufficient condition. So this is the gray area, correct? The necessary condition is utilization is lesser than or equal to 1, but I do not meet the sufficient condition, which is the U to be smaller than the utilization bound. Okay, now let's look at this example and we try to see how these parameters come into play. Now if I look at these 3 tasks, T1, T2 and T3, alright, and if I compute the utilization, that means if I say 40 over 100, okay, plus 40 over 150 plus 100 over 350, I will get this value here, 0.952. Okay, and that is greater than my B3. Okay, so for 3 tasks, okay, the utilization bound is 0.779. Okay, so we know that this is greater than 0.779. So we know that my utilization is lesser than 1 and now it's greater than my utilization bound, correct? So I'm now in the gray area. Okay, so I'm now in the gray area. So let's look at this and see how to analyze this. Alright, now let's simplify this and say that instead of 3 tasks, what if I only have 1 task? Okay, what if I only have task 1? So if I only have task 1, no problem, correct? I will definitely be schedulable because the utilization is smaller than the utilization bound. So if I only have 1 task, no problem, I'm schedulable. Okay, we are good. What if I add T1 and T2? Okay, if I add T1 and T2, also I'm still schedulable because my utilization is smaller than my utilization bound. Alright, now how about if I add T3 as well? Okay, if I add T3, then what happens? My utilization goes up and it becomes greater than the utilization bound. Alright, so once I add the 3rd task, alright, I am no longer fulfilling utilization bound, but I'm now in the gray area. Alright, so to understand this, we are going to explore what we call the critical instance of the task set. So what is the critical instance of a task set? It is the point where at the same instance of time, all the tasks are released. Okay, now why is this considered critical? Because if all the tasks are released at the same time, okay, that means if this one is the highest priority and this is the lowest priority, the chances of the low priority missing the deadline is quite high, correct? Because all the high priority tasks can keep on preempting. And the low priority tasks may miss the deadline. Okay, so at the instance of time where all the tasks are released together, that is what we call the critical instance. Okay, and this is basically the worst case scenario. Alright, the worst case scenario means all the tasks released at the same time and you're not very sure if the lowest priority task can actually fulfill the deadline. Okay, so how can we do this? Okay, so if I look at this here, the same example just now, and you want to analyze this. Alright, so let's look at the timing over here. So we have the 3 different tasks and the periodic interval. So this is what you want to do is you want to analyze and see whether for the lowest priority task, okay, C plus I is smaller than deadline. What is C plus I? In this case, C is the computational time of the lowest priority task. And the I is the interference. Interference means how much time all the higher priority tasks are going to interrupt me, are going to preempt me. Okay, if the time that I need plus all this interference is still smaller than my deadline, then I can make it. Correct? If my interference is too much, then I will miss the deadline. Okay, so that is the basic idea. Alright, so if we look at this, for the T1, okay, I have 40 units of time. Okay, each time I have a release of an instance. Same thing over here, 40 over here. Okay, and this is 100. So this is T2 and T3. So let's look at the interference. So within this time interval or time deadline of 350, how many instances of T1 must I release? 4 instances, correct? Okay, so I have 4 instances of T1 over here. This is the interference, correct? That means during the same interval of 0 to 350, 4 times T1 has already run, which means I need to set aside 4 times 40 units of time for task 1 to complete. Correct? Similarly, for task 2, 3 instances. So it is 4 times 30. So within the same interval of 0 to 350, 3 instances of T2 have already been released. Okay, that means I also need to set aside time for T2 to complete its task. Alright? Then I also need the 100 from here. Okay, so with this, we can see that the total interference is 280. Okay, this is the I. Okay, the total interference of T1 and T2, okay, that is going to affect the task 3 is 280, and plus the actual computation time of task 3 is 380. Sorry, is 100. So 100 plus 280 will be 380, correct? And that is already greater than the deadline. The deadline is 350, correct? Okay, so if I just look at these numbers over here, okay, the initial view is that is not possible, correct? Okay, the initial view is not possible because the total amount of time that I need is not enough to complete everything by the deadline. Okay, because the deadline for T3 is 350, but considering all the higher priority tasks that are coming ahead of me, I don't have enough bandwidth to complete everything. Okay, so it seems that it's not schedulable. Okay, but actually, if you look a bit deeper into the context switching that can happen, all right. So if you look at this, T1 is higher priority, so T1 will run first, correct? Okay, so when T1 runs for 40 units, immediately what happens? T2 can run, correct? Okay, so T2 can run means I can run for another 40 units. We know that the next instance of T1 is only going to come here at 100. And the next instance of T2 is only going to come here at 150. That means from here, which is 80 to 100, I actually have 20 units of free time, correct? Okay, I have 20 units of free time, which I can actually allocate to task 3 to run. Correct? So when that 20 units is up, okay, it's just nice for the T1 to have the next periodic interval. So again, I will have 40 units here. Okay, and so I'll finish at 140, which means that I have another gap here, correct? Because T2 only runs again at 150. Okay, so I have another small gap of 10 units here that I can allocate to T3. So when T2 runs, okay, it will compute until 190, and then I have another gap here of another 10 units, 190 to 200 before the next interval of T1. Alright, so when the next interval of T1 runs, I again compute for 40 units. This will finish at 240, and I will only repeat again at 300, which means I have another gap over here of 60 units, okay, for T3 to run. Now if I add up all of this, I actually get 100 units here, correct? Okay, and these 100 units are actually done within 300 units of time, not even 350. Okay, not even 350. By 300, I'm actually done. Okay, I can actually fulfill the deadline. All right, so there is something missing, correct, in the earlier analysis, correct? In the earlier analysis, when we look at all these numbers, we say that the total amount of time I need is 380, which is bigger than 350, so it's not possible. But when we go deeper, okay, into all the gaps, okay, between the context switching, we actually have enough slots to complete T3 within the, before the deadline in fact. Okay, so what is the missing part here in the analysis? All right, the missing part is we are actually able to complete everything by 300 means I actually do not need to factor in this and this, correct? All right, I don't need to factor in the last two instances of T1 and T2. In the previous case, we said 4 units, okay, because we factored in everything before the deadline. All right, but actually it was not necessary. Okay, we actually only needed to do until 300, and the last 2 units was not necessary. Okay, so that means that we cannot just rely on the deadline of that task to know this whether it's feasible or not. We need to do a bit more analysis, which is we need to check at more points. So what are the more points we need to check at? We need to check at all the periodic intervals of all the higher priority tasks. That means 100, 200, 300, 150, 300, and so on. Okay, so we cannot just say that the T3 350 check at 350. We need to check at all these other intervals of the higher priority tasks to know whether at any earlier point of time we are actually able to fulfill the requirement. Okay, so that is the thing we need to do, and at each of these periodic interval we need to check whether the demand is lesser than or equal to capacity. Demand means the computational requirement that the tasks are asking for, and the capacity is how much time has elapsed. Okay, so if I have elapsed enough time to fulfill the demand of all the tasks, then I can say that all the requirements have been fulfilled. All right, so if I look at this, okay, if I look at each of this periodic interval, at time t equals to 100, at time t equals to 100, you have T1, T2, and T3 being released. Correct? So T1 requires 40 units, T2 requires 40 units, T3 requires 100 units. So the total demand is 180, correct? And the demand of the 3 tasks is 180, but I only have 100 units of time that have passed. So I do not fulfill the requirement yet. Correct? Then I check at the next interval, 150. So 2 units of T1, 1 unit of T2, 1 unit of T3. So again, demand is greater than capacity. Okay? Again at 200, okay? When I compute everything, again the demand is greater than capacity. But when I hit T equals to 300, I find that it is just nice. When I add up the instances of T1 and T2 plus T3, it is exactly 300, okay, which fulfills the capacity. All right, so if I check at all these other intervals, I will have realized that at time t equals to 300, it is actually possible to schedule the 3 tasks without any issues with the requirement. That means all the tasks can actually fulfill the deadline. All right, so this brings us to the next schedulability test. All right, so this is basically what we call the necessary and sufficient condition. Okay, so I know it looks a bit scary, all right, when you look at all this. All right, so I'm going to go into the actual application, and then you will see that it's actually quite easy to relate. All right, but basically what we are doing is we are trying to compute, all right, the demand at all the periodic intervals. Okay, so let me show you how to apply this, and then it's easy to see. All right, so all I need to do is to sum up this. And what is this? This is the computational time, correct? So this is the C value. Okay, how much time I need to compute each task, and I need to multiply it by this, the ceiling of the current periodic value that I'm currently looking at, whether it's 100, 150, 200, or 300, divided by the periodic interval of each of the tasks. So if I'm looking at the periodic interval of 100, it will be 100 over 100. Okay, so if I just look at the first parameter, if I'm looking at the periodic interval of 100, then it will be 100 over 100. If I'm looking at 150, it will be 150 over 100. Then it will be 200 over 100, and so on. Okay, so the first parameter here and this parameter here will always be the same, right? Because they are tied to each of the tasks. The computational time and the periodic interval of the task. The only thing that will change is the numerator. And that numerator is basically at which interval am I checking. Okay, so I need to do this computation for each of the periodic interval. That means so this value will take on all of this. Okay, so that parameter will take on all of these values, which are the periodic intervals of all the higher priority tasks. Okay, and with that, if there's any point of time where we say that the demand, in this case the demand is smaller than or equal to the capacity, then we say we have fulfilled the requirement. Okay, we do not miss any deadline. Alright, so this is basically the final check. So if I can do this check and I can verify that at some point of time the requirements are fulfilled, then this is the gray area. Alright, so this is the final check for the gray area. That means I am smaller than 1, the utilization is smaller than 1, but I'm greater than the utilization bound. So this final check will be able to confirmly tell me whether it is still schedulable or not. Okay, so if I cannot find any periodic interval where the condition is fulfilled, then you can also conclude that it's not schedulable. Okay, so this is the final check. Okay, so with all of that, we just have these 2 more slides only before I go for a break. Okay, so until now we have looked at what we call the fixed priority scheduling. That means when I assign the priority, it is fixed throughout the entire duration of the system. Okay, now we're going to just look at one example of what we call dynamic priority. That means the OS itself has the ability to dynamically change the priority of a task while the system is running. Okay, so let's look at this example. So EDF is basically saying that the earliest deadline first. Okay, so whichever task has the earliest deadline will be scheduled to run first. Alright, so if I take these 2 tasks, T1 and T2, alright, so T1 having a earlier period or earlier deadline of 4 will be scheduled to run first. Okay, so in this case, T1 will run first, okay, and T1 takes 2 units of time. Alright, and after T1 runs, okay, so basically at this time T goes to 0, T1 and T2 are both released, correct? Both T1 and T2 are released, but the OS sees that T1's deadline is 4 units away, T2's deadline is 10 units away. Okay, so since the T1's deadline is actually earlier, I will schedule T1 to come first, or to run first. So once T1 completes, T2 will run. Okay, and then at the next periodic interval of T1, the next instance of T1 is supposed to launch. Okay, and as you can see, T2 actually requires 5 units of time, correct? Okay, so at this point of time, okay, when your next instance of T1 is about to launch, what will happen? Okay, the OS will come in again to see that for T1, the deadline will be 4 units away. But T2, the deadline is 6 units away. Correct? So the task with the earlier deadline will still be scheduled to run first. Alright, so in this case, I will preempt T2 and T1 will run. Okay, why? Because T1's deadline is 4 units away and T2's deadline is 6 units away. Okay, so the earlier deadline will run first. Okay, so after T1 completes, then I will be able to run T2. Okay, so while T2 is running, at again this time here, another instance of T1 will launch. Correct? So at that point of time, the OS will see that for T1's deadline, you still have 4 units away. But for T2, it is 2 units away. Correct? Because for T2, at this point of time, my deadline is here. It's 2 units away compared to T1, which is 4 units away. Alright, so because of that, T2 will continue to run. You will still be considered higher priority. Okay, when T2 finishes, then T1 will get a chance to run. Okay, and again, while T1 is running, at this point of time, we see that another instance of T2 will be released because T2's interval is 10. Okay, so when T2's next interval is released, but T1 is running, and you will know that T1's deadline is coming earlier compared to T2, which is 10 units away. So T1 will continue to run and then T2. Okay, when at this time T equals to 12, what happened? Another instance of T1 is released. All right, and again you will see that T1's deadline is earlier than T2. All right, because T1 is 4 units away, T2 is 8 units away. Okay, so because of that, T1 will preempt T2. Okay, T1 will preempt T2, and then it will run, and then followed by T2. Okay, now at this point of time, what will happen? T1 will also release an instance, and T2 is also running, correct? And what will the OS see? You will see that at this point of time, T1's deadline is 4 units away, T2's deadline is also 4 units away. Correct? Both of them have the same deadline now. Both are 4 units away, and because they both have the same deadline, we consider both of them to have the same priority. Okay, and since T2 is already running, it will continue to run. Okay, and then I will switch over to T1 after that. Okay, so this is an example of dynamic priority scheduling. Okay, that means the priority of the task is continuously changed during runtime, okay, by the OS or the scheduler. Okay, so it's called an optimal scheduling policy, and for EDF, you only need to check one thing, this. Okay, so U less than equal to 1 is a necessary and sufficient condition. Okay, necessary and sufficient condition. That means as long as I fulfill this condition, it is more than enough. Okay, I don't need to have any other check. Okay, because I'm able to dynamically change the priority. Okay, while the system is running. Okay, so it is called a optimal scheduling policy. Okay, so that wraps up the material that we have. All right, so I think we can go for a break now. Okay, so when we come back from the break, we will talk about the project as well as the exam format material. Okay, so in the meantime, any questions, you can come and ask me, or you can put in the poll. Okay, later I'll answer. Yeah.
T equals 11. How come T2?
Yeah. Sorry, this one. 11, this one, 11. No, because T2 already released here. Okay, so let's continue. Okay, so this is actually a robot made by one of your seniors. Okay, so one of the team members is here. Jared, you want to say hi to everybody? Okay, he's your senior, going to graduate soon. Currently on exchange, where? London. Liverpool. Any Liverpool fans can talk to him. All right, so he's back here for a short trip. Okay, so why is he here today? So last year, I was clearing a lot of stuff. I want to clear a lot of stuff from my house from here. So I had this old, not say old, fairly new drone. Okay, very nice to play with. So I say whoever is the top scorer for the module will get this drone. Okay, so he's the top scorer. Okay, so please give him a round of applause for last year being top scorer. Okay, okay, you can take the bag. Okay, so thank you. Enjoy your exchange. Okay, please follow the rules and regulation there. Don't get caught. Okay, bye. Okay, so you can see they actually custom make a PCB. Everything very nicely mounted. All right. So again, it's up to you. So some of them did this. Plus, he added some other nice battery pack and so on. Okay. So if you notice here, they have a reset button. Okay. Why they have their own reset button? Because the reset button broke. Okay, the robot toppled doing testing, and the reset button broke off. So they solder the wire out from the board and create their own reset button. Okay, so that's their own reset button over here. Okay, so that is the thing. Do I have a reward for the top student for this semester? Let me go and check what I can clear. Okay, so last year when I clearing, I saw this drone which I didn't fly after a long time. So I said, okay, I give it away. Okay. So I'll go and find. I think I have another different drone. Okay, so I'll see. Okay, so what you're going to do now? Okay, so I'm going to open up a quiz for you all. Okay, so on the canvas, I'm going to launch a quiz. I think it's already launched. Okay, so before we look at the quiz, I just want to show you something else which I took a photo of recently. Okay, so all of us take the MRT, correct? All of us take the train, and usually we every time see the display, correct? The display that tells us which line, how many minutes, which line, how many minutes, correct? And that's a normal thing. Okay, but I saw something which I think probably I'm the one of the few who managed to catch this. So I quickly took a picture. Okay, so this is what I saw that day. Okay, this is our own local train station. Okay, so what does this tell us? Okay, so why am I showing you this? Because this is, I mean, for a layman, they won't understand, correct? But we know this is a system level failure, correct? Okay, so when you all design your own system, correct, you must think of how to manage all of this, correct? Because the display is a resource. In this case, from looking at this, I can sort of conclude that the display is just displaying anything that comes out without doing any form of checking to see whether the system is properly booted up, is it in a safe state, okay, is it providing the correct information, anything like that, correct? Okay, so when you design a system, all right, don't assume that everything is always going to be perfect, correct? So a subsystem may need to wait for some acknowledgement, for some go ahead to say that, okay, my main system is booted up correctly, so now you can display the information. It should not be that I boot up only, I display everything that I want to show. Okay, so probably some system failure happened and you reboot and you just show this failure message without acknowledging or checking whether the whole system is booted up correctly. Okay, so that is just something, food for thought. Okay, so let me see if the Canvas quiz is open. Is it open? Let me check the Canvas quiz. Okay, so this is what is going to happen. I'm going to launch the quiz, okay, with some questions. Okay, I want you all to be very quiet and look at the code as if you're doing the exam. Don't talk to your friend, don't discuss. Okay, look at the code as if it's the exam time and analyze the code for yourself. All right, after we discuss, then you all can talk among your friends. So look at it and do it yourself without talking to your friend. Okay, wait, let me try to see. Okay, so look at the code, analyze first, then I will launch the quiz. Okay, so the quiz is published. Okay, so you can go to Canvas. There are 4 MCQ questions. And it's going to ask you what you observe when you run this code on your board. And I want you to think for yourself and answer, because this is how the exam question will look like. Okay, it will be some code, okay, where you're supposed to analyze based on the understanding and answer the questions. Okay, I'll give you all another 2 minutes, okay, to analyze and do the 4 questions. Okay, so let's see the outcome. Let's see the outcome on the board. All right, so the 4 questions basically ask us what is the first state, second state, third state, and fourth state that we observe, correct? Okay, so let's see the outcome first, and then we analyze the code to understand why we observe this outcome. So red, so the color is blue plus green, then red again, and blue plus green. So it's basically only these 2 different combinations, correct? One is red, the other one is blue plus green, and this continuously repeats. Okay, so this is the behavior. This is the behavior of the code. Now let's switch back to the code to understand why this is the case, correct? Okay, so we have the 3 tasks, correct? Red, green, and blue, correct? Red, green, and blue. So let's do that. Okay, so we have your red, okay, and then we create a semaphore here with this. 2, 1 means what? 2 is the maximum count, correct? 1 is the initial count. That means I have a resource which is maximum count of 2, but the initial count is only 1. Correct? Initial count is only 1. All right, so my semaphore, okay, so if I put my semaphore here, my initial count is 1. Correct? Now, when I run the code, what happens? Okay, so I first create LED red, followed by green, followed by blue. Correct? Okay, so the order is important. All right, because that will determine the sequence. All right, so when I run the code, okay, once I start the kernel, I will switch to multi-threading, which means the LED red will run first. Correct? So when LED red runs, what does it do? It tries to acquire the semaphore. Does it get the semaphore? It gets the semaphore, correct? Because there is 1 available. Okay, there's 1 available, which means I get the semaphore. So when I run, okay, I take the semaphore, okay, and then I switch on. Correct? I switch on the LED. Okay, that is the first red that we saw just now. All right. Now after I do that, okay, the next one that runs is what? Okay, so after I control the LED, all right, I release 2 semaphore, all right? Okay, so at this point of time, okay, while these LEDs are running and blinking and so on, the green and blue already run, correct? Because of round robin, both of them would have already run. All right, that part we know, because all are equal priority. So because they already run, the first thing that they actually try to do is they try to acquire the semaphore. Alright, but since the red already took the semaphore, blue and green did not get. Correct? So they did transition to run state, okay? Okay, but the moment they say take the semaphore, they become blocked. Okay, same thing over here. They run, they try to take the semaphore, but couldn't get, so become blocked. Okay, so there was a context switch to both of them, but they cannot continue because there was no semaphore available. But the moment I release these two semaphores, what happened? Both of them can become unblocked, correct? Okay, both of them can become unblocked, which means that eventually both of them will run concurrently to on. Okay, so when I release, so whatever happened here, then I release. Okay, and I release two semaphore means I effectively trigger both of them to run. Alright? Okay, so when the red thread releases both the semaphore, I effectively allow both of the green and the blue who are in the queue for the semaphore to unblock and run. Okay, so that allows that color that we saw just now, which is the blue plus green together. The turquoise color is that blue and green that we saw. Okay. Now what happens after that? Okay, so of course, after I release, what happened? After I release, I loop back here, correct? After I release, I loop back and I try to acquire the semaphore again, correct? Okay, but now there's no semaphore available. Okay, because the two that I released went to both blue and green. Alright, the two that I released went to both blue and green, which means when the red loop back, okay, when the red loop back is going to be blocked. Okay, so over here, when I loop back and I ask for semaphore again, I cannot get, so I'll become blocked. Okay, so here onwards, there is no semaphore. Okay, I become blocked because the two went to both the green and blue that were in the queue. Okay, so blue and green both blink together. We see the turquoise color, all right, happening together. Now, when both blue and green finish concurrently, then what happens? Green does not release any semaphore, correct? Okay, so green does not release any semaphore, which means that when the green loop back, there is no semaphore available also, correct? So when the green finish and you try to loop back, if there is no semaphore available, so it goes to a block state. Okay, so that part we know. So when I finish everything here, okay, so the details you know. So when I loop back and I try to do a semaphore again, okay, cannot. So I go to a block state. So this is block here. Here is also block. Okay, after I release the semaphore. Okay, the same thing, okay, for blue. When the blue also finish everything, what does it do? I release the semaphore. Correct? So when I release the semaphore, what happens? So here I run. Okay, when I run finish, I release the semaphore. But when I release the semaphore, who does it go to? It goes to red. Because red is the first one who asked for it, correct? Now red is the first one to ask for it. Okay, so when I release the semaphore here, it actually goes to the red LED. Okay, so when I loop back, I also got no semaphore. Okay, so when I loop back, when the blue loops back, there's also no semaphore available. So I go to a block state. Okay, which means that when I release, this will allow this to unblock. And then the whole loop repeat again. Alright, so the whole thing repeat again. So again, the red gets it blinks the LED, release two semaphore, green and blue concurrently unblock, blink together, and then blue release to allow red to continue again. Okay, so that is how the exam question will look like, in a sense. Okay, that means whether it's semaphore, whether it is mutex, event flag, message queue, okay, the idea will be the same. That means you will have code given to you to analyze, alright, and you need to analyze, alright. Now the important thing, okay, why I ask you to do the quiz? Okay, why I ask you to do the quiz is because this idea of what is LED state means is what you observe. Okay, what you observe means, even though technically when we say green and blue together, we know that it's actually one after another, correct? If I step through the code, we know that actually it is one after another, but we don't factor that in. As long as we see it together means we say it's together. Okay, so the LED state is the idea of what we observe with our eyes. Okay, so in our eyes, we cannot see that green on first, then blue on, or blue on or green on. We just see that they're on together. Okay, so the LED state concept means what you observe. Okay, and it does not factor in the blinking. That means it's not that I off then on. So the off doesn't matter. Okay, unless it is permanently off, then there will be an option that says it's permanently off, no LED. All right, as long as there is some color observed means there will be one of the color option. Again, the color option is based on what we observe. Okay, what we observe does not take into account that small amount of time for the transition for one LED and the other LED. Okay, as far as we physically observe is both the LED together. Okay, Ken? Does anybody have any questions on this? Okay, so again, the questions that you saw in the quiz, that sample question is also the same type you will see in the exam. Okay, what is the first LED state you observe, what is the second LED state? That means that gives you the idea of the physical observation on the board. Okay, so you must know how to do this. That means given the code, you must analyze the code, all right, and everything. So the exam, I will provide an appendix with all the OS kernel calls. Okay, it will be a closed book exam. Okay, it's closed book, but all these OS calls will be given to you. So you don't need to worry about the syntax and memorize anything, no need. Okay, the OS calls, everything will be summarized to you in an appendix. Yeah. No cheat sheet. No need cheat sheet, trust me. Your cheat sheet will confuse you even more. Okay, as long as you know the concept, you can answer. Cheat sheet will not help you, trust me. Okay, I spent 3 hours in the night, middle of the night, setting the paper, so I can tell you cheat sheet will not help you. Okay, so you need to know the concepts. Okay, cheat sheet will not help you. As long as you know how all this work is fine. Any other questions? Okay, I will upload the appendix so you know what is provided. I'll upload the appendix so you know what is provided. Okay, and you will see that all the OS calls are provided, so you don't need to worry about all that. Okay, so there's another question. Okay, so the coverage will only be from the OS part only. So there's nothing to do with whatever midterm covered. Okay, all the hardware programming will not be tested. Lecture 10 onwards, OS onwards. Okay, so don't worry, I will send an announcement with all the details. But basically, it will be lecture 10 onwards. All the first half hardware part will not be covered. Okay, only OS part. Only MCQ. Yes. Okay, the last few batches is all only MCQ. So you don't need to write code, you don't need to draw diagram, you don't need to do anything. Just understand the code and answer. Sorry? I can't hear you. Favorite letter? No, doesn't work like that. Okay, so anyway, tomorrow is NUS Wellbeing Day, correct? Okay, NUS Wellbeing Day. So for all your well-being, I have a lot of chocolates here. Okay, so please come and take. I think there's enough for each person to take 2. Okay, so come and take this before you go. I try to put here so it doesn't drop off. First come, first serve. Later don't say finish already. Okay, any other question you can come down and ask me. Then you can take 1 chocolate. I think there's enough for 2 per person.